lesson 1.1, power functions. Let's start with the little warm-up investigation there. You have what looks like ripples in water. A rock tossed into the water of a calm lake creates ripples that move outward in a circular pattern. The area, A, spanned by the ripples, can be modeled by the function area with respect to radius equals pi r squared. The volume, V, of helium in a spherical balloon can be modeled by the function 4/3 pi r cubed, where r is, again, the radius. The functions that represent each of these situations are called, what do you think? I'll give you a hint, it's the title.
Power functions.
They're called power functions.
Cool.
Power functions. Okay. So here's what a power function is. A power function is the simplest type of polynomial function. A power function is the simplest type of polynomial function. And it has, so a power function is the simplest type of polynomial function and has the form f of x equals ax to the power of n. Okay? Ax to the power of n. So here you have your variable, which is x, you have your coefficient, which is a, and you have your exponent, or your power, which is n. What's important about these things, comma, we always have qualifiers here, where x is a variable, a is a real number, so it's from the group of real numbers. It's not an imaginary number. And n is a whole number. All right, a power function is the simplest type of polynomial function, has the form f of x equals ax to the power of n. So you notice that it's only one term. That's the key. It's not going to have ax squared plus bx plus c. It's just going to be ax squared if it's quadratic. If it's a cubic, it's just going to have something x cubed. Okay? Good. And basically what I want to just note is, what's a whole number?
Number with no decimals.
Number with no decimals, yep. Positive integers, negative integers, and 0. Okay, so that's positive.
Aren't integers only greater than 0?
The group of integers, yeah, so it's just a way of describing whole numbers, if that's fair.
All right.
So if you took all of, well, if you can say this, because if you took the whole group of integers and you made them negative, you'd have these numbers. Does that make sense?
I see.
In which case you'd have the whole numbers.
Okay.
Yeah? Positive integers, negative integers, and 0. How do we write that as a group? Dot, 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 -2, -1, 0, 1, 2, comma, dot, dot, dot. Close out that bracket. Okay? Good. Some more notes for us. We're going to talk about what a polynomial function is, and then we're going to move on to just looking at more of these basic polynomial functions, the power function. So, polynomial expression. Just under there, you should have quite a bit more space, right? A polynomial expression has the form, polynomial expression has the form a sub n x to the exponent of n plus, and maybe you just look first and then you can jot it down, a sub n minus 1 x to the power of n minus 1, and this just keeps on going. Basically, all it's saying by this n minus 1, n minus 2 business is that that is the coefficient of the first term. This is the coefficient of, well, I guess you'd look at it backwards, but if you're looking at, let's say, something to the power of 5, then a sub n is the fifth coefficient. Okay? If you're looking at the next term, which could be x to the power of 4, then this would be the fourth coefficient, a sub 4. Okay, so a just represents a coefficient, and this is the coefficient that it is, and it matches the variable that is raised to that same power. Okay, now some of these, so let's say you had, let's not use 2x squared, let's use 3x squared plus x. This is a polynomial expression. This is raised to the power of 2, so this would be represent a2 equals 3. Okay, this coefficient is 1 and this power is 1, so a1 equals 1. And because there is no constant term, then a here, it's just coefficient of this term would be 0, because that term got multiplied by 0 and isn't there. If that somewhat makes sense. It's really just the general statement that a polynomial takes, polynomial expression. The keys are the exponents, the powers are in descending orders, descending powers of x. So you start with the highest power of x in a polynomial, and then the next term is less than that, and then the next term is the one less than that. If not, then they're in the wrong order, generally speaking, although it's still a true statement. We're good to kind of continue. It'll make sense as we go. We're going to take more notes on this, so it'll make a bit more sense as we go. Okay, then let's say we skipped a bunch and we just wrote, this is like a really long polynomial expression. We don't often deal with ones that are like this long, but it's just the general form. So then we have a coefficient of the cubic term, the x to the power of 3, and we have a coefficient of x squared term, and we have a coefficient of the x to the power of 1 term, and we have a constant term. Okay? So a naught represents the constant term. Okay, so let's jot down some pieces here. N is a whole number. X is a variable. Coefficients. The coefficients like a sub n, a sub n minus 1, all the way to a sub naught are real numbers. The degree of the function, is n. Okay, so you'd say an nth degree function in the general term. If the first term is to the power of 3, then you would have a function of degree 3. You'd have a third degree. Okay. The exponent of the greatest power of x is n, which is the exponent of the greatest power of x. Usually it's written in descending order, so that's pretty straightforward. A n, a sub n, is the leading coefficient. Leading coefficient is important to know about and remember. It defines, well, what does the leading coefficient define about a function? Let's just think simply of a quadratic. Remember, the leading coefficient determines whether it opens up or down. Something as simple as that, right? Stretch compression is involved there. It's the leading coefficient. And again, if the terms within the polynomial expression are in descending order, then a sub n will always be right there, the first coefficient. Okay, coefficient of the term with the highest power of x. Okay, a sub naught is the constant term. And then if we wanted to have a polynomial function instead of a polynomial expression, basically all you would do is, right now it's an expression. In order for it to be a function, you have to name it as f of x or something like that. And you'd say f of x equals this. Now all of a sudden it's a function that relates the y and x axis. And you could graph it. Okay? We won't make a note on this, but polynomial functions are typically written in descending powers of x, but they don't need to be consecutive. So you can skip terms or powers of x. So you might have, for example, you can jot down this as an example of a polynomial function, 4x cubed plus 2x minus 1. It's still a polynomial function, even though you notice there's no x squared term. Okay? Even a constant function, just f of x equals 6. It only has a constant. It's still a polynomial function. Okay, it's a polynomial function where the highest power of x is 0. See that? Anything to the power of 0 is 1, so that's just 6. Good. You could even write this, the general term for a polynomial function that is just a constant would be a sub naught x to the power of 0, right? X to the power of 0 is 1, so whatever your coefficient there is, that's going to be the value of the function. All right, let's look at, flip the page, number 1. We're going to look at those functions that are there and see if you can identify which equation matches which graph. Go ahead, take 30 seconds and see if you can match those up. Okay, investigation 1, we're just going to quick double check our answers. 1a, y equals x is linear, odd, so it should be going from quadrant 3 to quadrant 1. That's going to be picture number 4. B, if you guys want to remind me what they go through, 5. B is
6.
5 because it's just a standard quadratic, goes through 1, 1, 2, 4, 3, 9.
C is 6.
C is 6. We decided that it is odd, and it is the one that increases the slowest out of the odd ones other than the linear. D was picture number 3.
Yeah, 3.
Okay, goes through the origin, and then you can see 2 to the power of 4 is 16, and that goes through 216, so we're good. E is another odd one, y equals x to the power of 5. It's the steepest odd one, that's picture 1. And F, y equals x to the power of 6 is the steepest even function going through 0, 0, picture number 2. Okay, then you have a little diagram on the next page that shows key vocabulary. So we're going to go through all those things. Basically, you have power function, you have degree, and you have name. So y equals a. Well, if it's just a constant, then it's x to the power of 0, which gives it degree 0. What's that name? It's already given for you, constant. Okay, y equals a times x. Well, a times x, the variable is x to the power of 1. We just don't need to write that 1, so it's degree 1. And what kind of function is that?
So So linear.
It's linear. Okay, chase that, fill in that those boxes all the way down to the bottom, and then we'll review. All right, degree should be easy. If the exponent is 2, the degree is 2. So that column is really easy. What are the names? Natasha, what's the name for a second degree? Quadratic. Jacob, do you know, or Jake, do you know the name that we use for the power function that's raised to the power of 3? Yeah, we can just say raised to the power of 3, or we can also call it a cubic. So some of these ones have special names. David, for degree 4.
I'm gonna guess you'd say like tetric? Or
Yeah, you probably could say that.
I have no idea what the word is.
We use quartic.
Quartic?
Yeah, I suppose it depends on which root language you want to base your answer on.
Quartic.
And quintic is there for you, I think.
Yeah.
All right, looking over to the right, looking at your number line there. Basically, there are different ways to represent information. There's different ways to represent intervals of numbers, okay? So you have your brackets. That's one way. Bracket interval is one way to record an answer. That includes an interval of numbers. Then you have an inequality as a second way. You can represent the same thing. Number line is a third way. And then we have some words to describe it there. So if we're just going through that list there, when you have rounded brackets, it does not include the value, okay? So you have it from A to B, not including A or B, okay? Your inequality says the same thing. X is any number between A and B, but it can't be equal to A or B. So it's bigger than A, but smaller than B. On the number line, it's represented with an open dot at the value that marks the boundary. So you have an open dot at A, an open dot at B, but anything in between there is included in the values of X. So you can fill in the words there in the word column. Maybe that's the only thing I'll really record. Oh no, we have to do the number line as well. The number line is not done for you. So go ahead, where would we draw our line in order to represent the set from A to B but not including A or B? All we would do is draw a line between A and B. Okay? And then we have X is, what word is missing? It's greater than A and less than B. Okay, I'll do the next one with you as well and then kind of leave you to fill in the chart. So the next one, we have a round bracket around the A and a square bracket on the side of the B. The inequality tells us that means that X is in between A and B, but it includes B. It can be equal to B. So on your number line, and actually our first number line, I should do these in the blue as well. Circle those. Okay, so we're going from A to B. This time we're going to include B. So B gets a solid circle, A gets an open circle, and all the numbers in between are included. We say X is greater than A and less than or equal to. Less than, so your words that are missing is less than or equal to B. Okay, you go ahead and do it on your own, and I'm going to also continue doing it, and we can double check at the end.
In the middle of 3, you don't even have to do anything.
Let me know when you guys are done, and then we can just kind of check it orally. Key is to remember square brackets are inclusive, round brackets are exclusive. Good? Okay. Not going to do the whole chart then. Okay, on the bottom of the previous page, a couple of notes we still need to take. One has to do with end behavior, and one has to do with symmetry. So, a relation is a function if for every value of x, there is only one value of y. And the graph of a relation represents a function if it passes the vertical line test. So first note that we're going to do is vertical line test. A relation is a function if it passes the VLT, vertical line test. And really, I should have done these notes a little bit backwards. I should have said a relation is a function if it passes the vertical line test. That's probably good enough, actually. And then, and there is one y value for every x value. So x can't map to two different y's, right? An input can't have two different outputs. Two different inputs can end up at the same output, but you can't put 3 into the function machine and get 7, and then put 3 in again and get 8. That wouldn't work. That's not a function. Would not pass the vertical line test either. Okay? End behavior. Again, hopefully this is feeling a bit like review. But end behavior, we talk about as x approaches infinity, which is like this, as x approaches infinity. That's reading a graph to the right. And then we have as x approaches negative infinity. And that's x arrow negative infinity. That would be looking at the function from right to left. What's happening as x approaches negative infinity. Last thing is symmetry. So we've got line symmetry. This is when a vertical line, such as x equals a, divides the graph into two parts, two equal parts, let's say. Basically, the goal is that they're a reflection of each other. And I can draw a little diagram. But there's an example of a function that has line symmetry. Okay, so wherever this parabola is on the graph, on the grid, on the coordinate plane, this line, x equals a, is splitting the parabola into two equal parts where one is a reflection of the other. Okay. The other one is point symmetry. Point symmetry. And it is about a point A, B. What does that mean? That means you can essentially rotate, and if you rotate at 180 degrees, it'll end up laying on itself. So point symmetry about a point AB if graph can rotate onto itself when rotated 180 degrees. So that's going to be something like a cubic if it goes about point AB. Basically what we're saying is if we took this thing and we spun it around 180 degrees, it would land back on itself. Okay, what makes a relation a function? End behavior is just vocabulary that we use as x approaches infinity, moving to the right, and as x approaches negative infinity, that's looking at it to the left. And then line symmetry and point symmetry. Line symmetry can only happen in an even function, even powered function, and point symmetry can only happen in a odd powered function. And we'll get more specific about when those things can actually happen as we move along. Okay, let's pick up the pace a little bit here. We're going to example 1, sorry. Determine which functions are polynomials and justify your answer. State the degree and the leading coefficient of each polynomial functions. We just took definitions of a polynomial function. Just quickly, is A a polynomial function? G of x equals the sine of x.
Sorry, where are we looking?
Example 1 at the bottom of the next page. A says g of x equals the sine of x. Is that a polynomial function?
Yep.
Anyone agree or disagree? What kind of function is it?
Well,
It's a sine function.
It's a sine function, which is trigonometry. So it's a trig function. But look back to your definition of polynomial function. Remember, polynomial function is...
Can't sine be in place of A?
No, sine is not a value. It's a function in itself. Like it's
Okay.
yeah, it's a different relationship. It's not a coefficient. Remember, in a polynomial function, a coefficient, which could go in front of a sine function, it comes from the whole numbers. So sine function is not a polynomial function. So we go no. This is a trig function. B is f of x equals 2x to the power of 4. Is that a polynomial function? Yes. Follows the form. It's actually a power function, right? It's a simple polynomial function. Good. State the degree. So the degree is the exponent. So we have a degree 4. Then we get to state the leading coefficient, LC, which is 2. So it's going to be like a stretch, right? And that's it. That was easy. Okay. C. This one's for you guys. Y equals x cubed minus 5x squared plus 6x minus 8. David, polynomial or not polynomial?
Yeah, it is a polynomial.
It is. It's a little more complicated than a power function, but it is a polynomial function. Degree?
3.
Degree 3, thanks. That's the highest power of x. And leading coefficient?
8.
So that would be the constant. Leading coefficient is the coefficient of the first term, or the coefficient of the term with the highest power of x.
1.
Good, so we have a little invisible 1 there. And the last one, g of x equals 3 to the power of x. Polynomial function?
Nope.
Jake, what do you think? Is that a polynomial function or a different kind of function? Yeah, it's not a polynomial function because the exponent is in the variable, sorry, is in the exponent. Okay, so this is an exponential. Good. Example 2. Connect the equations and features of graphs and power functions. So for each function, state the domain and range, describe the end behavior, and identify any symmetry. So you have the pictures there in front of you. A is looks like this. And what do we got for domain and range? Any restriction on the domain? The x values that this thing takes? No restrictions, right? So this, every input is x belongs to the set of real numbers. That means there's no restrictions on what can go in there. Range, any restriction on the range?
X, y here, y set of real numbers.
Yeah, y belongs to the set of real numbers, so that means there's no restriction. This thing is, if it keeps on going left and it keeps on going right, it will also keep on going down and it will keep on going up. No restrictions. End behavior. So basically, what is happening as x approaches infinity, and as x approaches negative infinity. Let's look at x approaches negative infinity. So we would write that this way. We would say as x approaches negative infinity, what is y doing? So as all of our x values are going further and further to the left, where is y going?
It's increasing.
Yeah, it's going up. So it's gonna keep on going and going to positive infinity. What about as x approaches positive infinity, as it function keeps on moving to the right, to the right, to the right? Well, the y values are going down, 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 down. So y approaches negative infinity. Third thing we need to do is identify any symmetry. Is there point symmetry? Is there line symmetry?
There's both point and line symmetry. So point symmetry would be at 0, 0.
So let's say we'll start with point symmetry. Yep. Point sim about 0, 0, or about the origin. And let's think about line symmetry. Is there a line, a vertical line that this thing can flip over and be the same?
Y equals x.
So is that a vertical line though?
Yeah. Oh, vertical line.
Yeah, it has to be a vertical line.
Vertical?
So you're right, it can flip over that line and be equal, but it cannot flip over a vertical line.
Oh.
Right? Then this point would have to map to this point or something like that.
It is actually no.
So there is no line symmetry. There will never be both. Just so you know. Unless, I suppose, the equation of the line was y equals a constant or x equals a constant. A perfectly vertical or a perfectly horizontal line could technically rotate. So it would be to the degree 0. Anyway, let's not get into it. Second picture, second image for example 2. It is a parabola. You have the equation there, y equals 0.5x squared. And let's go ahead and talk about domain. Any restrictions on x? Or could you input any value of x all the way to positive infinity and negative infinity? Yeah, no restriction. Okay, parabola, if it doesn't have you know, a hole in it, and a line if it doesn't have a hole in it, no restrictions to the domain. Range. Restrictions to the range? Remember, it has to be greater than 0. So the range is all of the y values included in the function. So in this case, there are no values less than 0. It touches 0, 0. So we know y is going to be greater than or equal to 0. Okay? End behavior. As x approaches negative infinity, what is y doing?
Approaching infinity.
Approaching infinity. Good, positive, right? It's going up. And then as x approaches positive infinity,
Y is still reaching infinity.
y is still going up, approaching infinity. Good. And symmetry?
There's line symmetry.
Line symmetry.
Along the vertical, whatever you call it.
Thank you very much. Line symmetry in the y-axis. You could also call that line x equals 0. Good. Scroll up. C. Picture looks like this. Ish. And domain. Any restrictions on what we can put in there?
Just x here.
Yeah, x belongs to the set of real numbers. Range. Any restrictions?
Nope.
Nope. End behavior.
As x reaches positive infinity, y reaches positive infinity. As x reaches negative infinity, y also reaches negative infinity.
Good. And symmetry.
Point symmetry about the origin.
Point symmetry about the origin. Or 0, 0. Origin. Okay, so basically what are we doing? We're just describing characteristics of these functions. I'd like to quickly go through just one other way of noting end behavior. Another way of noting end behavior is to tell what quadrant it starts in and what quadrant it goes to. Okay, so this one goes from, and we would read left to right. Okay, so it's going from quadrant 2 to quadrant 4. So you say quadrant 2 to quadrant 4. That tells you what it's doing both ways. You know it's ending going this way and ending going that way. Okay, what about this guy? Quadrant 2 to quadrant 1. Okay, Q2 to Q1. That tells you that it's whatever it's doing, it's ending up in quadrant 2. So it must be going to positive infinity along the y-axis, okay? And the last guy is going from quadrant 3 to quadrant 1. Okay, so we would say it extends from quadrant 3 to quadrant 1. It's another way to note end behavior. For the majority of your work, both will be acceptable. Example 3, describe the end behavior of power functions. Write each function on the appropriate row of the second column of the table. Give reasons for your choices. So, which functions do you see that will extend from quadrant 3 to quadrant 1?
Y equals x to the 7. Because it's an odd power, it's going to do the same thing as cubic.
Yep, so the general shape, yep, it's going to be odd, just like a linear or a cubic, and it's positive. So that's how we know it's actually going from, if I can write my quadrants. That's how you know that it's going to go start down here in 3 and move up to the right, okay? Any other ones going to do that? Basically, you're looking for positive, odd. There's one more that is going to do that.
5x. No, not that.
Any other
There's negative evens, which is
how about that?
There's negative 3x to
2. But an even will start and end going the same direction.
Yeah, you're right.
Okay, so here we go. Next block, we're looking at Q2 to Q4. See if you can pick any out. Q2 to Q4. So again, it's going to be odd because it's going different direction. So if it's not the positive odd ones, it must be the negative odd ones. So go ahead and jot down the negative odd ones. We've got y equals negative 2/5 x to the power of 9 and y equals negative 4 x to the power of 5. Next, we're going from Q2 to Q1. So it starts and stops up. What type of function are we looking for?
Positive quadratic.
Positive quadratic would be fine.
Even exponent.
Even exponent.
Yeah.
So what do we have? We have y equals 5 x to the power of 6.
X to the power of 10.
And y equals x to the power of 10. The last end behavior, Q3 to Q4, which is going to be your remaining options, but to describe them, what are we looking for?
Negative even exponents.
Negative function, even exponent. So we've got y equals negative 3x squared, and we got y equals negative 0.5 x to the power of 8. Okay, and if you want to put a little note, you can say why they're each there. The top box from Q3 to Q1, they have an odd exponent, positive coefficient. Then you have odd exponent, negative coefficient, even exponent, positive coefficient, and the last one, Q3 to Q4, was even exponent, negative coefficient. Good, and example 4. Okay, so real world application of power functions. You have a volume function. Just like the spherical balloon that we talked about at the beginning of the lesson. We've got helium is pumped into a large spherical balloon designed to advertise a new product. The volume V in cubic meters of helium in the balloon is given by the function V with respect to R is equal to 4/3 pi r cubed. where r is the radius of the balloon in meters, and the radius ranges from 0 to 5 meters. Okay, so this balloon is being inflated, and basically the only part of the graph that we're interested in is the part where r goes from 0 to 5. So the horizontal axis from 0 to 5, positive values, which of course makes sense because radius can't be a negative number, and volume can't be a negative number. Okay, it can go from 0 and then increase. So here we go. We're going to graph it. In order to do that, we're going to make a table of values. So just quickly sketch out a table of values. You have radius measured in meters, and then you have your function, which is volume with respect to radius, v of r, equal to 4/3 pi r cubed. That is going to be measured in meters cubed. And we're only interested in the values from 0 to 5, so we'll stick with whole numbers. 0, 1, 2, 3, 4, 5. We're going to be graphing this by hand. Obviously, you could put this in Desmos and graph it that way as well. And basically what we do is we take our value of r and we plug it in. Okay, so for the first one, if you have 0 radius, how much volume are you going to have? 0. Okay, plug in 0 for r, 0 cubed is 0, 0 times anything is 0. Okay, when we put 1 in there, we can do as much as we can in our heads, but basically you have 1 cubed, which is 1. So you have 1 times pi times 4 divided by 3. And just to save us a little bit of time, 4.18, so we'll round that to 4.2. Okay, for our value of 2, we put 2 in there. We get 2 cubed is 8. 8 times 4 is 32. 32 pi divided by 3, which gets you approximately 33.5. Always good practice to get your calculator out and see if your calculator still works. Next one, we put 3 in there. 3 cubed is 27. Times 4 times pi divided by 3, we end up with approximately 113.1 cubic meters. And for the sake of time, I'm just going to plug in the next ones. With a radius of 4, we end up with a volume of 268.1 cubic meters. And with a radius of 5 meters, this balloon has a volume of 523.6 cubic meters. Then you are able to graph it. Sorry you don't have a little template of a graph there. So you can draw your own little quadrant 1 graph. We're going to range from 0 on the r axis to 2, 3, 4, 5.
It's kind of crazy how a balloon that's 10 meters wide has an area of 523
cubic meters. Big boxes of air squished in there.
Something like that.
Something like that, eh? Our biggest number is 523, so I'm going to go up to 600. Cut it in half. 300. Cut it in half. 150. 450. And plot my points. Plot our data. We've got 0, 0. You've got 1, 4, which is pretty negligible there. 2, 33. 3, 113. Well, it's doing something. 4, 268. And then 5, 523. Way up there. Ish. And as you pump air into it, it is continuous, right? It's going to, everything in between, the radius could be anything from 0 to 5, not just whole numbers. So that is going to be a continuous graph here. So we'll draw a line. And it doesn't get an arrow at the end because it actually does stop at r equals 5. And we could label our axes. Radius measured in meters. Volume measured in meters cubed. Domain and range.
Axes are 5. Right, so right, x belongs to a set of real numbers, and x is equal to or greater than 0, and equal to less than 5.
Yeah, can I give an easier way to do it? So let's write it that way, sure. So 0 greater than or equal to x 5. Okay, another way to write that, second way, r belongs to the set of numbers, interval notation, from 0 to 5 inclusive.
Oh yeah, that's how you had it up there.
Okay, let's try it again with range. I'll write it the way that we're more familiar with. And then you guys try to write it with bracket intervals. And this, we should actually use V, right? V instead of Y, because it's the V axis, the volume axis. Anyway, volume belongs to square brackets from 0 to 523 inclusive. Describe similarities and differences between this graph and the graph of y equals x cubed, which would kind of look like that.
This looks kind of like the first quadrant of the x cubed graph.
Yeah, basically what we've done is we've taken some transformation of the first quadrant. Differences, we don't have any range or domain less than 0. You don't need to make any specific note on that. Okay, as you'll find out always, the key concepts on the last page of the lesson in your textbook are really helpful. It's basically a summary of what you already have in your notes, but that's on page 11, and then your practice problems are from page 11, numbers 1 through 7 and 11. Again, I'm not going to check your practice problems, so do what you need to do, ask questions on what you need to ask questions. The only way to learn math is to do math, and your grade is your responsibility, so do your best, and I'm more than willing to help any way I can.